Hi, I'm Bryce.
I'm Zach. And we are here trying to explain to you how we came up with this project to have a robot that plays ping pong.
That's right. We were sick of having to need a partner all the time to play ping pong, so we have effectively developed a robot arm to play ping pong with us.
Yes. We've captured the ball on camera and then used image processing to calculate trajectory and then move the robot servos to meet the ball in mid-flight.
Here's our project. So the webcam that we're using is the Logitech 200 webcam, and we actually have two of these. This camera here is capturing our X and our Y data. It's Z and Y, isn't it? That's what I said.
You didn't say Z.
What do you do? And this camera captures Z and Y data for our arm here. We also have a second Logitech 200 webcam here at the base of the arm, and this captures our X and Y data. And these two cameras are calibrated with an origin right here at this point, in between this shoulder servo.
The way the servos move lends to a spherical coordinate system where position is determined by angles. So the best thing to do, like Bryce said, is to place the origin right at the center of movement, that is, the shoulder servo.
And what the cameras do is they're able to look at a binary image that has just the ball in it. And from that image they can correlate the data that they have and give us an actual point in 3D space of where the ball is. And then using that point, we can pass the data to our servos to control where the arm should go to be able to return the ping pong ball.
Each frame of video is just a photo. OpenCV takes each frame, smooths it out, and stores it as an RGB or red, green, blue image. That image is then converted to an HSV, or hue saturation value image, which in its raw form looks something like this. We then specify which HSV values to look for by giving it lower and upper bounds. Any pixel whose HSV values lie within those bounds are turned white, while all other pixels turn black. The result is something like this. From here we can calculate where the center of the white object is and have it give us an XY value in terms of pixels. That data must then be converted to an actual position on the ping pong table. We can do this by graphing the camera data versus the actual data and then finding the equation for a best fit line. And MATLAB can do everything for us.
The Maestro.
So we've got three servos here. The first one is like a shoulder theta, and it has this motion. The second one is a shoulder phi movement, controlled like that. And the third one is an elbow phi, which moves this elbow joint here. We need to capture two data points. With these 2 points, we can calculate the velocity in the x, y, and z directions. Velocity can be calculated by dividing the change in position by the change in time. Once we know the velocity, we can plug that into position equations. These equations express positions as a function of time, or in other words, we can find the position of the ball if we plug in a specific time. We need to find the time t when it will intersect with the yellow plane. The way we've set up our coordinate system, this will be when z is equal to 0. Solving for t gives us this equation. Now that we know the time t when the ball will hit the plane, all we need to do is plug t into the position equations, and that will give us an xy position where the ball will be when z equals 0. The paddle will need to be positioned here if we are to successfully deny the ball passage to the other side. As stated before, the most natural coordinate system to use would be spherical, which consists of rho, or the distance from the origin, phi, which is the tip-out angle, and theta, which is the rotation in the xz plane. This picture shows the things which we know and the things which we need to find out. We know rho s and rho e, which is the yellow and pink lines. They're the lengths of the arms, which we can measure. We can obtain x and y from our cameras. What we need to find is phi s and phi e, or the white and the teal angles here, because that's the data that we need to send to the servos. We're going to keep theta constant, mainly because it just makes things more simple. With a little help from the law of cosines, we can come up with these equations. You should probably take some time to study them and see if you can come up with them yourself. Because inverse trig functions have a finite domain, the actual computations given really depend upon which quadrant the ball will land in. Here's the quadrant-specific equations to find phi s and phi e. It may be different depending on what you call the origin and which directions you designate positive and negative, but this is what worked for us.
You're live. Our ball was traveling too fast to be detected by our cameras when thrown. So to solve this problem, we attached the ball to a curtain rod so that we could simulate a slow-moving ball. Yeah. When the ball is too far away from the center of the camera's frame, the data actually can become skewed because the camera thinks the ball is either closer or further than it actually is. One thing that can happen is the ball can pass too fast for the camera's frame rate. So the ball can pass literally in front of the camera and the camera will see nothing. And the way to solve this is to use high-speed cameras. Using high-speed cameras to be able to detect the ball multiple times as it passes, no matter what speed it passes at.
Well, that's our project. Hope you enjoyed it.
Thank you.